Hi everyone, welcome to the Earth Science Classroom. This is the EM Field video 3, which is in the outer core, and it's in the Earth Science Earth Interior series. And I want to begin with the outer core. So I'm going to draw myself an outer core. There's an inner core right there, outer core there. Okay, so we have the iron, we have the nickel. We know that it is moving, and there is turbulent convection through the heat transferred from the inner core to the outer core, and there's primordial heat and decay of different isotopes, and you have this immense heat pressure and an awesome environment. And you have this circulating, convective, moving, molten, millions of tons of liquid iron alloy, basically, and this is basically the Earth's geodynamo. Now, a dynamo is something where you would have an induced electrical current, and you'd make the magnetism go around it, like a coil around it, and basically, it's the same thing that happens in the outer core. You have the solid inner core, which the outer core is wrapped around, and the movement is around, but then you get this huge amount of magnetism going out and back around and in, and out and back around and in. And this would be thousands of times. And basically what you'd have is, because of the alignment and organization of the molten iron alloy, you get the generation of this self-sustaining and maintained electromagnetic field, which works the same as a dynamo, basically. And in simpler terms, you have this on the right-hand side here, this bar magnet, and you have the movement from it's basically is always a dipole situation. Dipole, di means two, pole means separation of polarity between negative and positive within either the atom or a larger material, and you have the movement away from the north and into the south, away from the north and into the south. So what you have is pretty much a simple bar magnet is working very similar to that of the outer core, which is exponentially larger. And these kind of spraying out bits of magnetism are called magnetic fluxes, and they can also range in what's called magnetic density. These lines, or these invisible energy fields of magnetism, can overlap, they can join together, they can get smaller, get larger, they can definitely fluctuate in space and time. And this is why the EM field is such a complicated thing, because it is constantly in motion, it is constantly changing, it is constantly on a large revolving cycle, like most things are on the Earth, where the actual polarity can switch, and it's called a polarity reversal. It happens every 200,000 years. But these fluxes that are generated from the outer core are so large that they actually extend out of the outer core, beyond the mantle and the crust, and outside our atmosphere into the space around Earth. So if I draw my Earth in the center here, and I draw these lines that are representing the magnetism, the invisible force of magnetism that is created from the outer core, it actually would do this. It would basically, it would overlap and come out like this. And it'll be like this bunch of overlapping small loops, and they would go away from the north and in at the south pole. And also these points where you would call it the magnetic North pole, basically, it's not geographic, but it's magnetic. It is 11.5 degrees off the actual axis tilt. That does actually change as well, and the actual position geographically of this North Pole on the magnets actually moves. It actually moves, and we can actually date it moving over areas of North America, Canada, Russia, Greenland over the course of the last few thousand years. It moves quite substantially. But it's this tilt and this huge amount of magnetic fluxes which extend into space. Now it extends pretty much around 6 to 10 times the radii of Earth. So put that into layman's terms, let's do 10 times. So radius, so 63,700 basically kilometers into space around Earth. So let's take our atmosphere. Atmosphere is technically about 150 to 250 kilometers thick. So this is way off past the atmosphere into what's called the magnetosphere. Now, technically, this is part of the thermosphere, along with other layers as well, like the ionosphere. And this pretty much is constructed by the outer core. It is the invisible force field or electromagnetic fence, so to speak, around the Earth that goes into space, and it has a very cool interaction with our sun. So you take this image of the sun, obviously it's not to scale, but the sun to the left and the Earth in the center, and these red lines represent the magnetosphere and the fluxes. What you'll have is there's an area right there. So as the sun's radiation is coming at basically a solar constant, and you have this consistent amount of energy from the sun pouring towards the Earth. And within that array of energy, the EM spectrum, you have some nice radiation, and you also have some harmful, not very nice radiation that the sun gives us. Now, these also include solar flares, which happen often on cycles, and also the solar winds, which can harm Earth if allowed to reach our surface or atmosphere. However, this beautifully constructed, awesome piece of nature that we had no control over and no idea existed until only recently in our timeline is the actual magnetosphere, which is created by the outer core and the ion and the convection and the movement. It produces this electric fence, this invisible field, this shield, this force field, which would, when it hits the sun's radiation, is called a bow shock. And it'll be right here, bow shock. It's like a battering ram. It takes most of the brunt of the force. It's like in Star Trek where they said raise your shields. It would basically shield the Earth from a battering ram of energy that's harmful from the sun, which could cause the Earth damage. There's a natural defense for the Earth. And it would squash the magnetosphere because the sun's energy is very powerful. So it would be a distance of between 5 to 10 radii. Okay, oh, there's an A in there. So, but however, because of like comets, where you have the tail of the comet that's kind of like trailing off into space whenever it's going towards the sun, this tail is called a magnetotail. Can extend up to 1,000 times the radius of the Earth off, away from the sun. So this could trail off for a very, very long distance. And the sun's energy is then pushed over and it basically is protected by what's called a Magneto Sheath. So in terms of like a electric wiring, there's a sheath that would actually insulate or protect the actual wires. So the sheath is the exterior magnetism, which is basically redirecting this sun's energy away from the Earth. Now, some of it might hit Earth, but definitely not nearly as much as if we didn't have an EM field. Like some planets don't have an EM field. Now, there was a recent article come out that about 42,000 years ago, the EM field has shown evidence to weaken or even switch throughout 1,000 years, and that the effect of that and the allowing in of UV or even gamma or X-ray radiation from the sun in these winds, and the concentration of this energy would cause havoc with our ecosystems, soils, uh, hydrology, and basically they're suggesting that a lot of large mammals went extinct during this period in time because of the weakened magnetic field. So obviously more research has to be done into the effect of this and if and when it's going to reverse in the near future. But this invisible force field, which is made by the outer core, is absolutely amazing because it's one of the things that has allowed life to flourish on this planet. Not only is it a decent distance in the Goldilocks zone with the right amount of water and the right atmosphere and the right size, but also the right temperature, but also it has this EM field because of the amazing outer core, which is constantly convecting and turning and moving and have the self-sustaining geodynamo that creates this EM field, which naturally protects us. So thank you, outer core. We appreciate it. Guys, also, if you appreciate this video, please subscribe, and we appreciate the support, and look forward to seeing you in other videos.